Hi students. So today we are going to start a discussion about Kepler's law, and there are essentially three laws which were propounded by Kepler, and these are actually very fundamental laws as far as space mechanics or orbital mechanics is concerned. So today's video we are going to discuss that. This is lecture 63 in our course. I'm Dr. Ranjan Ganguly. Now at the end of this video you should be knowledgeable about the Kepler's laws. So let us look at the first law, and Kepler's first law postulates that a satellite essentially describes an elliptical path around its center of attraction. So what this means is something which comes from our previous couple of lectures, which is that typically if you want to orbit around a given planet, you need to follow an orbit which is elliptical, and this happens when E lies between 0 and 1. Remember that the case E equal to 0 is a special case of the ellipse when both these axes are the same. That is A equals B, or the major and minor axis of the ellipse are equal. Now you can visualize various situations. For example, if we look at the Earth, you have an orbiting satellite. There are many orbiting satellites at any given moment of time. These satellites are doing various kind of communication activities. They are also involved in weather forecasting and so on. There are also satellites which are giving you the coordinates of wherever you are located. So these are the satellites which use triangulation and give you the GPS coordinates. Now beside GPS, which is given by the US, there are satellites which are given by different countries also. For example, there is GLONASS system by Russia and so on. Now, whatever be the orbit, we have seen that it can be represented by this general conic section formula, which is in polar coordinates, the polar coordinates being r and theta. E is the eccentricity, and P, of course, remember, is h square by k square. So the first law is very obvious from all our previous discussions, and this means that whenever there is a satellite around some body such as a planet, it is going to go through an elliptical path. So now let's come to Kepler's second law, and Kepler's second law says that in equal times the areas swept out by the radius vector of a satellite are the same. So if we look at a typical orbit, which I have given in this red here, and we look at the center of the body or the earth, the distance is some r. Now the angle here is d theta, and therefore the area of this arc is going to be given by this particular size here. So let us do some basic geometry and get an estimate for A. Now we know that dA is going to be equal to half r dh, and this comes from the fact that if this dh is small, this is essentially like a triangle, and you are getting this from the basic definition of the area of a triangle. Also remember that dh is r d theta, and this is coming from our definition of d theta in radians. Now combining these two equations, I can get dA is half r squared d theta. I divide this equation by dt, so I get dA by dt is half r square d theta by dt, which is half r square theta dot. Now recall from our previous discussions about the orbit equation, we know that r square theta dot is a constant, and therefore dA by dt is a constant. So that's the mathematical form of the Kepler's second law. It looks somewhat more cumbersome when you actually write it out in English, but the math form is very simple. That is, dA by dt is constant. Now, what does the Kepler second law mean? We can try to visualize it. For example, let's take the Earth here and let's take an orbit of the moon around the Earth. Let's say moon is the satellite here. Now, what happens is that there is going to be a situation where the satellite is going to move faster whenever you are closer to the Earth, and it's going to be slower when you are at some distance from the Earth. And this happens because the areas here, which I have given in this blue, are going to be equal because dA by dt has to be kept as constant. So the practical fact which comes from Kepler's second law is that the satellite has higher velocity nearer the Earth and the satellite has a lower velocity far off. We can show this in a different way. For example, let's again take the Earth and the orbit of a satellite like the Moon. Now, if you are at some location here where r is lower, then the velocity is going to be more. If you are at a location where r is greater, then the velocity is going to be less. So here I have made this in terms of r far, v near and r near. And what it means is that v near is going to be more than v far. So this is a fact which actually Kepler observed. So all these Kepler's laws are based on observations which he was able to do while sitting on the Earth. So at the time he was doing all these things, there were no space vehicles out there. This is the basic fundamental of space mechanics, which is through observation and experimental physics. Now let's look at Kepler's third law, which is the complicated one, and we need to prove this today. So we are going to derive this equation. So what Kepler's third law says is that the period of any two satellites about the same planet are related to their semi-major axis as tau 1 square by tau 2 square equals a1 cube by a2 cube. So this is the equation here, and of course 1 and 2 refers to satellite number 1 and 2. So here tau represents the time period and a is the semi-major axis. Now in case you have forgotten, for an ellipse the semi-major axis is this bigger axis which is given by A, and B is the semi-minor axis. Semi simply means it's half of the complete distance here. Now remember, if you were dealing with a circle, A would be equal to B. Now let's define some more notation which we are going to use today. So essentially, if we consider the Earth, we consider the Moon here, then the distance which is maximum from the Earth here, you can see this is known as the apogee point, and the distance where the distance is lowest, this location here, this is known as the perigee point. So essentially from mathematical perspective, we can say that there is a value r min and there is a value r max, and this would be the distance from the Earth to the satellite, the maximum distance, and the Earth to the satellite, the minimum distance. One thing of course you can immediately see is that r min plus r max is going to be equal to 2a. So this is going to help us to calculate a also. We are going to use that in the next few slides. So now we are going to get estimates of r min and r max. So to do that, let us return to the orbit equation, and for simplicity we will simply assume that the phase C is 0. So the orbit equation reduces to this simpler form. Now what we can immediately see is that in the orbit equation P was h square by k square, and therefore R can be written as h square by k square 1 plus E cos theta. Now we are going to take this equation for R, which I just discussed in the previous slide, and we are going to consider various facts. One of course is that E is less than equal to 1 because we are dealing with an ellipse, and now we can think of the maximum and minimum value which R could take. Now of course you know that cos theta is going to vary between -1 and 1. So the lowest value cos theta can take is -1, and therefore R max would be when this value cos theta becomes -1. So we get 1 minus E. Now remember that E is always greater than 0 also, so it lies between 0 and 1. Now similarly R min would be given by h square by k square divided by 1 plus E, because this happens in the situation when cos theta is maximum, that is cos theta is 1. In that case you would simply get 1 plus E. So now we know R min and R max, these are the two values here which are given, and these are the values which are the maximum and minimum distance between the Earth and the satellite concerned. So now we are going to take R min and R max value which I calculated in the previous slide, and I'm going to calculate the value of A. So A is half of R max plus R min, which you can get from this geometry here, because 2A is going to be R min plus R max. So I simply write down these two equations here in this form, and I then do some algebra. So 1 minus e into 1 plus e gives me 1 minus e square. I get 1 plus e here, I get 1 minus e here. There is a cancellation of this plus e and minus e, and I'm left with 2. The 2 and 2 cancels here, and I finally get a is h square by k square divided by 1 minus e square. So this is an important formula. Need to remember this for further use in our derivation today on the Kepler third law. So now we are going to use some facts which come to us from coordinate geometry for the ellipse. Now one of the fact is that the area is going to be pi AB. Now you of course remember that for the circle is pi r square, and in the case of the ellipse you can show from calculus, from integration, from definite integrals that a is pi AB, and so that would be the area enclosed by this figure here. Now there is one more formula which we are going to use, and that relates the eccentricity with AB, which is given in this yellow box here. Now what I do is I simply square both the sides, so I get e square a square is a square minus b square. I can then write b square in this manner. So this will tell me that b equals a 1 minus e square to the power half. So this formula in this yellow box is very important. It is a formula which comes out of the basic theory of conic section for the ellipse. If you are more interested in this formula, you can take a look at any coordinate geometry book or any basic math book. For example, those taught in the first and second year in college or in the freshman and sophomore years. So essentially now I can take a is pi ab, and I substitute b here from this equation, and so I get a is pi a square 1 minus e square to the power half. So this is the area of the ellipse expressed only in terms of a, which is the semi-major axis, and the other thing it has is it has e, it has pi. Of course you know pi is 3.14159. Now let's further continue our derivation. We have this equation from A from our previous slide, and now we consider again the fact that dA by dt was half r square theta dot is half into h. H was r square theta dot. This is coming from the orbit equation which we did quite some time ago. And essentially now what we are going to do is we are going to take this equation for dA, which is half h dt. We are going to integrate it. So we are going to take the fact that t varies from 0 to tau, that is one time period, and then the area is also going to go from 0 to a as we go around that particular figure. So from this equation I can write a is half h tau, and then I have a already here, so I can write these two a's are both same. So I equate the half h tau to the pi a square 1 minus e square to the power half, this equation here. And also I keep in mind that a itself is given by h square k square by 1 minus e square. So we are going to use these two equations in the next slide. So now I take the equation for A. I already obtained this equation relating H, A, E and K, and therefore I can easily move forward here. So what I get is A is half, H tau is this equation. These are both nothing but equations for A. Now what I can do is I can equate these two here. So essentially by equating these two I can get several cancellations. So after getting those cancellations I get a much simpler form here. Now if you are confused about what I have done here, just take a look at this part, half h tau. So I put half h tau here, half, this is h and tau. Okay, so this part here goes here, and then the pi a square 1 minus e square to the power half part goes here. So these are essentially both expression for the area A, and after I have these two expressions I can do some cancellation. For example, the 1 minus e square term can be cancelled, and then I square both sides, so I get 1 by 4 a tau square k square equals pi square a4. So I get it from this equation, and therefore I can write tau square is 4 pi square a cube by k square. Now you can immediately see this is a constant into a cube. So this is the equation which we have been searching for a long time. I'm going to write out this equation here again, and now you clearly see that this equation is very important. It essentially relates our time period to A and K. Now, if there are two satellites, let us say 1 and 2, and I will have two equations which will involve tau 1 A1 and tau 2 A2. Let's say the planet is the same, so K remains the same, in which case I could divide these two equations and I'm going to get tau 1 square by tau 2 square is A1 cube by A2 cube. So this equation in yellow is the Kepler's third law. So Kepler's third law derivation is one of the favorite questions of many aerospace engineers and physics professors. So I would say it's good to know this pretty well. And the derivation is not simply given because they want to mess the student's life up. It actually gives you an insight into the various different formulas which are involved in this calculation. So it's also something which will make you develop a good respect for Kepler for having come up with this law very long time ago. So let us again summarize the things we have learned today. The Kepler's first law was simply that the orbit of a satellite around a body such as the Earth is going to take an elliptical path, and you can see this around the solar system. If you look at the sun, the different planets are orbiting around the sun in this kind of path. If you look at the Earth, the satellites or the moons are in this mode also. If you look at Saturn, if you look at Jupiter, if you look at any planet, all the moons are essentially going through this elliptical orbit, and that's why prediction of where they are is all very easy because they all follow mathematics like clockwork. Now, Kepler's second law was that dA by dt equals constant, and we saw that law also what it physically means. It actually means that when you are nearer the Earth, for example, you speed up more, and when you are farther, you are at lower speed. And the most important third law, which can be expressed mathematically, is that tau 1 square by tau 2 square is a1 cube by a2 cube, and essentially this relates the time period of the satellite to the semi-major axis A of the elliptical path. Now, though we have used K here and we have made pictures of Earth, you can obviously understand that if the K is different, these laws would be applicable in any solar system out there or any different planet which has satellites revolving around it. So Kepler's laws are very general. The only place where the planet is coming in here is through this P, which essentially has h square and k square. And remember, k square is capital G into capital M. That's where the gravitational constant comes in, and also the weight of the planet or the mass of the planet comes in. So P is the place where the physics enters into the mathematics for this particular problem. So I have put a spacecraft here or a flying saucer just to show that these laws are valid wherever you are in the galaxy. So that was the end of Kepler's laws, and at the end of this video you should be familiar with the Kepler's laws. Now it is very interesting that Kepler's laws are something which is applied even today to all satellites and to all planetary motion. These were discovered a long time ago. So if you are more interested, you can delve deeply into how Kepler got to these laws by looking at some of the information you can get in Google, for example. So we will continue on this space journey. We are going to start talking about the ballistic equations and so on in the next few lectures, and I will see you then. If you have any comments on the videos, please put them in the comments box. I am trying to make them as simple as possible, and I also try to keep all the equations correct because I type them myself. But do keep in mind, if some mistakes are there, please point them out to me so I can bring them to the notice of others also. So I'll end this video now, and I will see you in a lecture sometime soon. See you then.